our lecturers from Germany. You know, Germans, they stick on time, very punctual. Okay, so I don't want to give him any bad impression of what we do here. So, by way of introduction, as I was walking here, I want to introduce what you guys all know, Professor Dreizler, but still I want to introduce. I think I want to introduce in terms of sort of one of the, okay, you remember. So one of the major problems in physics, you guys all know, is turbulence, right? Big unresolved problem. So that's one. And then one of the most challenging problems in combustion, of course, is turbulent combustion also. Or one of the major challenges in turbulence is turbulent combustion, right? And one of the major challenges in turbulent combustion is experimental turbulent combustion. Clearly, if you want to do it right, you want to really do it in, get the details and all that, that's turbulent combustion. And one of the best experimental turbulent combustion person is Professor Dreizler. So, that really puts everything in a nutshell, that I think it's how lucky we are to have him come all the way from Germany with plane delays and all that to give us the lecture. And Professor Dreizler, again, as I said, is one of the leading experimental combustion person in the world, in the whole community. So he has won many honors and recognitions, and I just want to mention one. He is the recipient of the Leibniz Prize in 2014. You guys all know Leibniz, and this Leibniz Prize is among one of the most prestigious recognitions in science, right, in the world, and of course, particularly in Germany. They got different disciplines, but in here, he is the one. So again, just we're really, really fortunate to have Professor Dreizler to give us the talk. So for the next 5 days, enjoying the subject area, and I told him he is totally in charge of our lectures. If he says that no break, no break. Okay, just sit here and listen, just enjoy. But he said he will give you breaks. All right.
Okay. So thanks a lot, first of all, for these kind words, and of course the introduction. I really enjoyed it. Yeah, welcome, and thanks for joining. I'll try to enjoy you, as he said, for 5 days, 3 hours each day, and give an introduction into advanced laser diagnostics. Maybe I should start with some words where I come from, and then maybe it becomes clear that you have to apologize for my German accent. Most of you probably have not been, especially to Darmstadt, which is located in Europe. I guess you know where that is, with Germany being here, and Darmstadt being somewhere here in the valley of the Rhine, which is a medium-sized city, typical for Germany, with something like 150,000 people living there. Small for most of you in the US, I guess. And special about Darmstadt is we have in the order of 40,000 students in more than 30 research institutions being there. So TU Darmstadt, the technical university, is one of the largest there, but as well we have the European Space Agency, as others that might be known to you. Here are some impressions. So it's a historical town. Although it was more or less completely destroyed in the Second World War, some of the old buildings have been restored, as you can see here. And sometimes actually we have as nice weather as you have with blue sky. Not so often, but it's right this time of the year okay. TU Darmstadt is one of the leading technical universities in Germany, linked to TU9. So 9 leading technical universities have joined. We have in the order of 26,000 students, and there might be another difference to what you're used to. We have only 280 professors. So the share between professors and students is in the order of 1 to 100, which is very different to most other countries in the world. However, we have here some more numbers about research associates and employees. The focus actually is on engineering with 50%, and there is one profile area devoted to energy conversion, and their combustion still is included. We do not know how long, but for the moment, that's still a very strong part of it. Mechanical engineering itself, you see over here, we have 3,000 undergraduates with roughly, again, the same share, 100 to 1 or even worse here with 27 professors, and third-party funding in the order of 50 million, meaning that each professor has to run a large group and has to bring in a lot of money to pay for all these PhD and postdocs. And in our country, a PhD is paid like an engineer, a beginner engineer in industry. So you really have to bring out a lot of money to pay for it. And that's why it's not only me directing the institute. I have people helping out in that. You see the list of people here. Some of them might be known to you from papers. And with this crew, we are looking for 25 to 30 PhD students. And of course, that needs to be financed. That's why a lot of my time is spent actually in trying to get money to run that group, which is here, as you see, as well as why you have subscribed for this course, I guess. It is about turbulent combustion using laser diagnostics. Okay, so that is my introductory. So you know about a bit. I would like to know from your side here, who is doing experimental work? Okay. And who is doing CFD or numerical? Okay. Good that you're here. And maybe you understand then afterwards why you have to be really careful in taking all the data that you might need for validation and understand where all the pitfalls are. Okay. So I think we can do that very fast. Why we have to still work in combustion research. So it's still clear that combustion technology is the dominant process for energy conversion. And that is here shown for coal, natural gas, and oil, pointed out. That is still increasing, although the share from 80% might over the decades decrease slightly. But for sure, this is a long process taking a lot of time. We have limited resources, that's clear as well. We are facing global warming. Most of the scientific people think that is due to fossil fuels and other sources made by man. We have, of course, pollutant emissions. We have had this scandal about diesel emissions, NOx and soot. But there is as well another reason why combustion research, in addition to these well-known reasons, is really important. So if you're thinking of the energy transition, going from a fossil more to a sustainable delivery of electricity, well, you are facing a problem which is due to the intermittency of sustainable energy production. For example, wind. Here you see a typical chart over 1 year where you see the load variation shown in red from electricity produced by windmills. And you have somehow to compensate these huge jumps. And that is where combustion can kick in and provide possibility for load flexibility to keep a constant net. And that is, in my country, a very important aspect where we have to have more flexible, load flexible, but as well fuel flexible combustion technology. And that needs research and a more detailed understanding. So I think the needs for efficient and clean combustion is very clear, but in addition, you need this flexibility. And because it's such a complex process, there is not only one view that will solve that problem. So that's why my strong belief is you really have to work coherently with experiments, theory, modeling, and simulation. And that's why I think it's very important as well that in this group, here some people from the modeling side and the simulation side are present. With only their expertise, we can as well ask the right questions and as well build up those experiments that support our understanding. So what is the objective of this week? First of all, of course, we will see in all the examples as well the role of combustion diagnostics, and this will be as well some more thoughts about in the first chapter. I will provide some basic insights about light-matter interaction here and there. Of course, not going into the details, for example, in spectroscopy, meaning quantum mechanics. By the way, anyone took courses in quantum mechanics here? At least a few. Okay. For the others, I try to give you that knowledge and insight that you need to understand the principle of the different diagnostic techniques. And then, based on that, I will discuss the most important diagnostic methods that are used in turbulent combustion, but as well, of course, can be used in laminar flames as well. And at the end, but not only at the end, but as well during the course, I will always spread in application examples to better demonstrate what the technique is good for. Of course, questions are welcome, so I'll try to answer those. If they are too long, maybe we have to postpone them then to the breaks. So we are facing a number of chapters. After the introduction, I will discuss some benchmark experiments, and that is as well as specifically important if you go for validation and understanding phenomena in combustion. So you have to have good designs of experiments to really answer those questions you have asked. Then we will see what are the general requirements that an experiment has to fulfill that you can apply these optical diagnostic methods. After that, we will go through these different methods for velocimetry, for thermometry in the gas phase, at surfaces of combustors, switching then from temperatures to concentration measurements, and discuss some more recent advances in volumetric imaging, three-dimensionally, as well as then implementing the time as a parameter, what we call then 4D or quasi-4D imaging. And I will have, as I said, in between all the time some examples, but later this week we will have then a focus on flame wall interactions. That's something I've been interested in since a number of years now. If time allows, I can as well discuss some new insights we have gained from effusion cooling and gas turbine combustors. And even if you have even more time, I think we don't get there, but probably we do. I have as well examples for technology development based on laser diagnostics in IC engines. Okay, with that, I would like to start with some more insight what the role of laser diagnostics in combustion can be. So what is the context? So first of all, you can classify where you can use this methodology for. The first is, if you have built up suitable experiments for that, you can study phenomena. Phenomena like, for example, flashback in gas turbines, or cyclic variations in IC engines, or turbulence chemistry interaction leading to a pollutant formation, things like that. A second aspect, which is very often building on this understanding on phenomena, is to build up systems that provide comprehensive data to be compared to numerical simulations. And that is very important, and just a few groups worldwide are doing that, but it has to be kept in mind. If you take, for example, codes like Fluent and do a combustion simulation with that, these models, interaction models, and predictions are compared or made become possible only because they have been compared to a number of benchmark experiments where you have access to validation data. Of course, there are as well other issues where you can use these kind of diagnostics directly for development of technology. That is typically done, as you will see later, because of costs in industry. And here we provide more the understanding of the methods and transfer methods to industry and not directly do that at university. As well, this kind of methodology can be used for control purposes. Yeah? If you, for example, want to understand or have a change in your fuel, you need a robust sensor looking for some parameters that your control system can react on that. And here, optical sensors can be as well a good choice. Okay, why have we seen over the last, let's say, 20 years or so, a constant increase of this methodology? Well, there are a number of enabling technologies where we take advantage of. So the most important are listed here: cameras and lasers. Very often they have been developed for very different purposes. For example, for material processing, in case of high-speed lasers or cameras, the advent of good quality CMOS cameras for high-speed imaging have been developed for crash tests, for example. as well as recent advances in digital image processing, for example, are just attractive to our field, and we exploit them and make advantage out of that. That is one part of the context that enables us to do the experiments we are doing. And of course, there are a number of related research areas. And so, as Ed Lowe yesterday told you, it's very important to not only stay into one field, but expand that, especially in combustion. That is true anyhow. If you apply now optical diagnostics as well, you need some knowledge about spectroscopy, chemistry, fluid mechanics, and heat transfer, to name the most important ones. So you see, this is quite rich, and you have to have a certain knowledge from different areas to perform such research and become successful with it. Okay, so what are the primary parameters of interest that we are trying to measure? So again, this is something like a short summary of the most important aspects here only. In turbulent combustion, of course, the most important aspect is the flow field. Without knowing about the turbulence properties, you're lost. That's why you have to start, if you really want to understand such a complex flow, with single point statistics, meaning you have to measure mean velocities, ideally all three components, and fluctuations from which you as well then can deduce shear stresses. As a next level, once that is done, it can be helpful to have some insight about parameters that are built from derivatives, meaning at least you have to measure at 2 points. Very often, as you will see by PIV, you do it in more than that, to get access to strain, dilatation, and vorticity. Although you already have to be careful, these gradients are difficult to measure, and what you access only is an apparent gradient, because your resolution that we need to discuss a bit further later on, your resolution might not be good enough to get the real gradient. It can be as well very important and helpful to get an idea about the length scales and time scales that are deduced either from single or 2-point correlations, and that as well give access to power spectral densities. To get the spectrum of a turbulent flow as a very important quantity, but you see them very seldomly. It's very difficult to measure these quantities, and it takes time. After that, the most important properties are then to have access to some properties of the scalar field, meaning chemical species concentration and temperature, where you as well are interested in single point statistics, mean and fluctuations, but as well you can gain insight from qualitative information, structural information that you deduce from, for example, imaging radical like the OH radical to see where a flame front, for example, is. That can be used in conjunction, especially with flow fields, to come up with conditional statistics, yeah? Meaning that you can condition a flow property relative to a flame front. And that is as well a basic idea I tried to follow for some years, which gives you more insight instead of only looking separately at these different parameters. Scalar gradients, very important for combustion modeling. For example, scalar dissipation rate in non-premixed flames, but as well extremely difficult to measure because based on gradients. And all you can access is an apparent gradient, and you really have to make sure that you're not blurred by a spatial resolution which is too coarse, or by a signal to noise that might be not good enough to really get this quantity correct. And then that showed up as well in the recent years. Although you might investigate a flame that looks like detached from the nozzle, actually you have always heat transfer in any kind. And if you want to understand the near nozzle flow, you need as well some information about these nozzle temperatures in case of enclosed combustion, of course, as well for losses of heat due to walls. Very important as well, and that is neglected to my understanding very often in many publications, that the inflow and boundary conditions have not been documented well. It makes a huge difference to build up a flame in a Friday afternoon. It will burn for sure, but you might have no control about these inflow and boundary conditions, and then you might see certain phenomena and processes which are strongly influenced by these boundary conditions. And if you don't have any idea what they are doing, you're lost again, which means that a lot of work, in my view, at least that's what I expect from my PhD students, goes into a good design, into a good characterization of these boundary inflow conditions. More recently, if you refer as well to industrial needs, unsteadiness became more and more important. So for example, cyclic variations in gasoline engines with direct injection are one example, not well understood, but you need good experimental methodology to look at them, because you cannot rely on CFD in that. CFD is not in a position really to predict what an engine is doing, and so here we see a clear benefit if you support at least these theoretical approaches by solid experimental methods and well-suited engines that allow to mimic what is actually happening in a real engine. Okay, this list, although not complete, already is relatively long. And what we do is to exploit optical diagnostics in the sense that we use light-matter interaction and transfer methods that have been, of course, developed in physics and physical chemistry to engineering science. And that's quite interesting to see as well. When I started my career, early 90s, most of combustion, or a lot of combustion in Germany was done in physical chemistry, and that stopped completely. Yeah? Most of the physical chemistry chairs have been devoted to more advanced biology, material science, and things like that. And gas phase physics is decreasing. Maybe different in the US, but I think that's not good. However, what happened is that engineering science took that over, to a certain extent at least. Yeah, we are measuring by light because we can directly measure inside the combustor, and sometimes we are really non-invasive. But that is true only for a few diagnostic techniques. In most other cases, we have at least a system that is minimal intrusive. Okay, we have very high temporal resolutions due to the fact that we can pulse laser radiation, and there is, due to the way these lasers work, 10 nanoseconds is not a problem, and 10 nanoseconds, as you will see, is short enough to resolve all the scales we are interested in. But that is different in the spatial domain. Due to the working distance you have to fulfill with your imaging system, for example, let's say 200, 300 millimeters or so, your spatial resolution often is worse, much worse than 10 microns, such that at high Reynolds numbers, where you have very small scales, you cannot resolve them. So you filter very often in turbulent combustion diagnostics the parameter of interest, which makes it difficult to compare as well with results from CFD. So here's the list of the methods. Partly we will look at them, not all of them. We will have a short look into laser Doppler velocimetry, where you can measure in principle up to 3 components in a point. And a point means something like a ½ millimeter minimum in beam direction and maybe 50 to 100 microns perpendicular to beam direction. We will look into particle image velocimetry that can be run as well at high speed, not only in a plane that is 2D. Yeah, it can be as well operated volumetrically, 3D, and you have the choice in how you do it, measuring either 2 or 3 components. Two-phase flows, a very complicated problem where our diagnostics have not really evolved as much as in other fields, especially in gas phase diagnostics. So still, of course, you can do something like Mies scattering to look for spray penetration, things like that. You can use phase Doppler anemometry to look for particle diameters if they are spherical, but that's it more or less. There are some developments going on worldwide, very specific to look as well in very dense sprays, but the success is limited, I would say. So still, if you want to have a breakthrough in diagnostics, I think here that is an open field. Scalar field measurements. Some people have used Mies scattering, so they injected to one of the flows particles and then observe the mixing. That is good for large structures, but typically you're interested as well in smaller structures in mixing, such that Mies scattering is not really a good choice if you want to go into the details. People have relied on laser absorption spectroscopy, and you will see that's a very powerful technique, but it's line of sight. So in turbulent combustion, it is limited in its use. You need a certain spatial resolution that comes from laser-induced fluorescence, commonly used qualitatively, quantitatively very complex because of the quenching, because of the fact that you have collisions after the electronic excitation of a molecule with gas molecules from the surrounding. Raman-Rayleigh scattering is a very, very good choice to become quantitative, and we will talk about that for concentration measurements. But although it has been clear in principle for many, many decades, it is at single shot to get really instantaneous realizations of a turbulent flame really difficult to apply because it's a fight against the noise. Yeah? Signal to noise is always very limited. Then Korean anti-Stokes Raman spectroscopy, we will see about that as well. That is a technique that has seen a revival the last 10 years, especially triggered by researchers in the United States based on ultra-short pulses, such that this is a really powerful technique, although rather expensive. And the last, thermographic phosphor imaging that can be used for surface thermometry. I will talk about that in quite some detail. But as well, more recently, it has been used as well for gas phase thermometry, where particles have been suspended to a flow and then give access to temperatures of the gas phase, and as well can be used simultaneously in principle for particle image velocimetry. So that's the list of systems or diagnostic methods. And it's interesting to see as well where all has been started. And so most of these techniques I'm referring to and restrict myself to came from understanding of unconfined gaseous flames. So a very famous example is the Sydney Sandia burner with the flame series A to F, where a lot of these techniques have been applied, or more recently the stratified flame that received some attention, where Cambridge University and ourselves in Darmstadt, we have provided some insight into these kind of complex turbulent flames. However, what we currently see is that the whole field is moving on more and more to practical combustion systems, meaning that the idea is to mimic real combustors, for example in gas turbines, where you have enclosure, high pressure, and there it becomes relatively complex to get a good optical access, and even worse maybe, because that can be solved by good design. You have high turbulence levels, meaning that your length scales are getting smaller and smaller, such that you resolve less and less. And here you see some view graphs from DLR in Stuttgart and our own system, where I will show as well some examples. Multi-phase systems, that's another level of complexity. So I already talked about droplets and sprays. That is, I think, a very open field, especially when you go for high pressures into transcritical conditions. Not much has been done there. Interesting to see as well that solid fuel combustion has not been really investigated in depth, such that here for biomass or coal combustion as well an open field exists, where you can make a good contribution, although you might not directly dig into the most complex diagnostic systems. And another complexity that has been ignored for whatever reason for a lot of long time is the interaction between combustion and walls. This is as well something that has been investigated primarily for heat transfer, but the impact of the wall upon the turbulence chemistry interaction, for example, on pollutant formation and so on, although it's known, it's important, it has not been studied in detail. So that is as well something where you have additional complexity and a rather open field. And the last point here is complex fuels. So most of the studies have been done with surrogates or very easy fuels, starting with hydrogen, methane, but already if you switch to, for example, DME as a fuel that is still rather simple in terms of chemistry, from spectroscopy, it can be rather complicated. You have spectral interferences, you have unknown properties of these molecules in the context of light-matter interaction, to give some examples. Sooty flames can be the consequence of more complex fuels, as well as high optical densities, where then you have to deal with problems like absorption, for example, of your signal and it's very difficult to compensate or understand the inaccuracy coming from that complexity. Okay, so now I would like for this introduction to give some more ideas about what I mean about these 4 different tasks. So as you might remember, the first task I see for laser diagnostics in combustion is to study phenomena. And so at least the way to do that is that you have a practical problem in mind. It could be something like a process in an IC engine that is here taken from a view graph from Bosch. For example, flame propagation after the ignition has been initiated by a spark. So you have very often flame propagation in a stratified mixture. Studying that directly in an optical engine, don't do that. It's a waste of money. So you have to extract somehow the most important properties of this complex problem over here and transfer it to a canonical or more simple problem. And here you see a possibility. I've taken that from Nondas Mastarakos, where here you see a fuel jet propagating into ambient air where you have stratification. These lines are showing different isolines of stoichiometries, where you have here a certain location where the flame has been initiated, and then you can follow the contour of the expanding flame in a stratified mixture. And so this would be the way to do it. So you have to come up with good canonical experiments mimicking the most important properties. Then, once you have that, very often you need to adapt a certain technology to measure the parameters of interest. Sometimes even you have to develop that. And here, as I said already, I think we have profited enormously from the rapid developments we have seen in laser and camera technology. And all you have to do is to monitor that, to see what's coming on the market and try to use it for your purposes. And that enabled us to switch from single parameter measurements in the past to multi-parameter diagnostics, and that is a very, very important aspect. Turbulent combustion cannot be understood by measurement of single parameters. You really have to go for multiple parameters to see for correlations. Only then you get an idea about the interactions and receive a certain understanding. We see as well that measurements have started typically at point measurements with a certain resolution and are now on their way to volumetric measurements. We will see some examples over here. And it started as well statistically independent. That means that you have weighted at least 2 integral timescales, very often much longer. 10 Hertz is a typical scale, meaning that you have 100 milliseconds between adjacent measurements, such that you have statistically independency. But understanding cyclic variations, flashback, blow off, and things like that, they need really statistically correlated measurements, and they became possible only by kilohertz repetition rates. However, even if you have done all of these things and solved it, and maybe measurements of multi-parameters in multi-dimensions, the ultimate goal in this area is really that you work closely together with people, if you don't do it on your own, to sum up the knowledge you gained into physically consistent and ideally predictive mathematical models. That must be the ultimate goal, that we receive here a description that allows us in future to become predictive. And that is not yet achieved. Okay, task number 2, validation data. As I said, experiments can help to understand the fundamentals, phenomena, that are then hopefully comprised into models. But then the show must go on, because you need then to validate what the predictions, or the results I should better say, of large eddy simulations, or sometimes still RAND simulations is. So validation data is very, very important. Only then you can start to trust the results of these simulations in a certain parameter range, which is then used for direct technology development. We see as well that direct numerical simulation expands very rapidly, and as well it complements experiments. In experiments, of course, you never get this full set of parameters you in principle have access to at DNS calculations. However, until now, DNS mostly is restricted to small areas, where you have not the range of scales as in real combustors or engines, and it's limited to rather low Reynolds numbers. So I think ideally you should think about joining up with people doing the DNS and having here complementary information from different scales and Reynolds numbers. And then that can support model development and as well validation enormously to come up in the end with a better combustion system. Okay, if you follow this task of validation data, it is very important that you not stay with a single geometry. So my belief is you have to go from simple to complex, meaning you have to follow a stepwise approach where you start with the most important sub-processes to study, and then build upon that your comprehensive model. And examples of specific sub-processes are, for example, turbulence chemistry interaction. That has been the topic for many years in the TNF workshop. Soot formation, very open. Spray breakup, where as well a lot of things have to be done with reduced models to be implemented in holistic models for the whole system. And so you see here the strategy I follow in my institute, going from simple to complex, where I mean simple is something where you have an open flame, you have a rather simple flow field, like in a post-jet, where you have oxidizer against fuel. Chemistry, of course, might be or is complicated all the time. Another example of a rather simple setup in terms of flow field might be a jet flame, for example, a stratified flame that emerges here from a set of different jets coming out. The level of complexity increases if you're now still staying with an open flame, but have some recirculation, more complex turbulence, maybe due to a bluff body or a swirl or both. Or complexity might increase if you stay with a simple flow, like a jet. This is a fuel jet into a vitiated air, but here the interest is maybe more on the low temperature chemistry, ignition, auto-ignition device processes in turbulent flows, not very well understood and investigated. The complexity might be increasing if you go to two-phase systems. As I said, in sprays, especially to go into supercritical or transcritical conditions, has not been explored very detailed. And so here you see a system where single droplets are initiated at very high pressures, 60, 70 bar, and temperature is very close to the critical temperature where the surface tension goes to zero, and you have a change in your evaporation over a surface to a mixing. Or the complexity might increase if you add a wall, where you have interactions between turbulence and the wall, and as well between chemistry turbulence and the wall. That is very important for engines with ever-increasing volumes because of downsizing. Yeah, or here you see then where all these things have been mixed together, where we have then enclosed combustion with high turbulence levels, wall, flame wall interactions, and so on. Even with intermittency, switching to an IC engine, that is as well studied in my lab, and more recently as well, which is maybe the worst, coal flames, where you see over here, self-sustained coal flames where we more or less know no details. And that is a very challenging and open problem. And I think here globally, although maybe in the Western world coal combustion will decrease, biomass combustion will stay in importance, but as well other countries will need to build up their electricity system based to a good part on coal. So understanding that process better is as well very helpful. Okay, let's come to task number 3, support of technology development. If you look at the costs you have to build or come up with a new product at the market, we're talking about billions of euros. That's nothing a university can do. That's not our business. So our business is here to develop methods and support industries by providing the knowledge how to use those techniques and educate well-trained engineers who are then going into industry and use that knowledge for this new kind of engines. And so in this context, it is the transfer which is more important, as I said, by well-educated people, and that is typically done in my country by bilateral projects, which we have with different industries. And finally, task number 4 is to develop robust sensors. Here as well, optical diagnostics can contribute. But of course, here you need very reliable components, and that's of course not a bulky laser system like a neodymium laser combined with a CMOS camera or something like that. It must be really applicable to real-world systems, and that's why these systems need to be based on fibers. And that can be very nicely done in connection with absorption spectroscopy, where you can come up with devices like that, where you have a sensor, for example, integrated to a spark plug, or you can think of using the systems in exhaust pipes to see and monitor online what is going on with the combustion system, and use that for control purposes. All right, that's my introduction, and I would like to open the floor for any questions you might have. It's not the case. Then we can directly switch to the second chapter.
Can I ask a question real quick?
Yes. Oh, sorry.
Can you go over what Reynolds stresses are quick?
Reynolds stresses, if you have a velocity component uy, let's say the axial and the radial direction, you're interested in the fluctuations, which are due to the Reynolds decomposition. You take the actual value, which is decomposed into the mean value and the fluctuation value, and we're referring to the fluctuation values. If you now take, for example, the fluctuation value of the axial component and the axial component, or for the stress, the axial component, let's say, with the radial component, and then do the average, that is the Reynolds stress. Yes. So you have diagonal elements, axial, radial, tangential, and you have the off-diagonal elements, which are the mixtures between the three. And these are statistically mean values, okay? You need to measure them based on the instantaneous velocities. So you need to resolve really the time scale such that you have instantaneous values. Yes?
You said that measuring or trying to characterize direct injection by using an optical engine would be the wrong way to do it, and that it would be better to use a canonical setup.
In the beginning, of course, yes.
So why is that? Why do you say that would be a waste of money?
If you directly start with the characterization in the engine, you have additional problems. Different pressures, you have a very complex flow field overlaying to that, such that you might not really be able to extract what you're interested in, where it depends on the question, of course. If you're interested in engine-like things, you need to use an engine in the end. But if you're, for example, interested in how the propagation is influenced by the local stoichiometry or by gradients in the mixture fraction field, that is not measurable simply in an engine. Yeah? That level of detail you will never access, such that you might come up with speculations, but you will not have the detail that you need to really understand to answer these questions. Of course, if you're interested in the specific conditions that are imposed by the engine, then you have in the end switch to it. So what I meant, maybe I should make that clearer. You should start with a canonical system and then stepwise increase the complexity by adding more features, like, let's say, a crossflow, for example, that adds things that are beyond the original question you have asked. Okay? Okay. Let's have a look now, closer look into benchmark experiments. So those are important to understand phenomena, but especially as well to come up with validation data that are needed for numerical simulations. So you need access for the most important sub-processes that are listed here. What you see is a holistic model of a turbulent combustion process, where on the one hand side, you need a good chemistry that relies on detailed chemistry. On the other side, you have transport, turbulence, and mixing, including as well molecular mixing, of course. That is on its own a very complex problem. And what makes combustion so interesting and difficult is that transport timescales and chemistry, the scales of chemistry, are partly the same, such that you have a strong interaction. You cannot solve first the turbulence and then the chemistry, you have a strong interaction. And that needs here a good models for turbulence chemistry interaction itself. As I said, that has been the topic for decades or for 20 years now in the TNF workshop. You need as well submodels that account for heat losses, maybe directly by wall contacts, but as well by radiation. And in case of spray combustion, in case of coal combustion, biomass combustion, you have to handle as well the two-phase flow. So there is now a number of things that has to be looked at for which it is good to have then isolated experiments to look individually on these different aspects and not everything together in a real complex system. So what you need is really comprehensive sets of data. Comprehensive means velocity plus scalar field plus inflow and boundary conditions known. Eventually as well, this transients I have been speaking before if you're interested in certain aspects here. And so these reliable and comprehensive sets are can be gained by the diagnostics I'm going to talk about here. However, they can be done only when you have a suitable benchmark configuration. And as I said, that mimics the real world problem, but more isolated. So what is the requirement that needs to be fulfilled? Of course, you need an optical access. That's trivial. Typically, you need 3 optical accesses to your system. And that can be problematic in terms of high pressure combustion, for example. Why do you need 3 of them? You typically need to bring in the laser, but you do better if the laser comes out again. So you need a window to get rid of it to prevent or reduce stray light, for example. And then very often, because you're interested in a high spatial resolution, you're looking from the side with your detector, and that's why you need a 3rd window as well, perpendicular to the laser beam direction. You have to access somehow the nozzle. If it's a simple system like a jet, already there, you would like to come as close at least as a millimeter to the nozzle, and those of you who have done that, that is really not easy to fulfill. If we go to more complex systems, and we will see some examples, for example in flashback, where all of the story is happening inside the nozzle, you need as well optical access to the nozzle itself. And that is seldomly done. In case of atmospheric flames, you have to make sure that you're not influenced by your lab. That's why we very often operate with co-flowing systems. But that is as well something, it sounds trivial, but guarantee that in your lab, make some investments where your supervisor wouldn't like. You have to decouple the flame from the exhaust system. That's the same story. And you have to select a fuel that is compatible with your diagnostic technique, because you have to avoid any kind of interference that would make your interpretation of the signals very difficult. And this is an open field. Yeah? Already if you switch to, as I said, DME or other fuels containing more carbon atoms, we do not know too much about spectroscopy there. And you need to clarify that first before you can really dig into the application of the techniques to understand what's going on. Okay, what are the requirements for a validation sequence? So as I said, I stress it again, you have to know or you have to measure the inflow conditions. And already when you think you have built up a good jet, better check it whether it behaves as you expect as a fully developed pipe flow. It needs to be rather long to really fulfill this requirement. And if you can't afford that, measure the inflow conditions. That's my recommendation. You have to define the boundary conditions. You have to go with the flame sequence where you vary the most important parameters, because if you have just a single flame that can be as well used for validation purposes, that's useless, I think. You really, what you can expect as a minimum of a CFD calculation is what we call if-when. You somehow always tune the knobs in the CFD. All right, aren't they? And then once you have tuned them, at least for this geometry, you should predict what happens if you change a key parameter. And that is then only possible if you have a flame sequence. And so parameters of interest can be fuel composition or equivalence ratio. It can be Reynolds number. That's always a problem in lab flames. Reynolds numbers are rather low because you might not have the exhaust system that allows for higher thermal loads. And If you stay with only, let's say, Reynolds 5,000, 6,000, that might be a problem. The best is if you speak to those people, at least 10,000, better 20 or 30,000 in nozzle exit Reynolds numbers, and then you easily end up with thermal loads in the multi-10 kilowatt regime, which is difficult to handle. Swirl intensity can be a good parameter to be varied, pressure, or sometimes even geometry. So all about that is identify sensitivities. What are the crucial parameters that are influencing the system you're interested in? And out of this sequence that I have built up in Darmstadt in my labs, I will choose here 3 benchmark flames and the example of the optical engine to demonstrate a bit more clearly what I mean about these canonical systems. So for a long time, opposed jet flames have been in the focus of interest. Here you see a realization of that. An opposed flame means that you have 2 nozzles that provide, in a non-premixed configuration as here, oxidator, that is air, and fuel from the other side. Typically, you operate them with the identical momentum at the nozzle exit, such that both streams impinge at each other and form a mixing layer in the statistical mean, at least here in the central plane. You can use that as a laminar flame, but as well by inserting grids over here and here, you can make the streams turbulent. And here's the most easy way to generate turbulence. That's just a hollow plate. It's maybe not the best choice. Today I would use it differently. However, what you see here is a system that allows to bring up the turbulence level to something like 7%. If you have a fully developed jet flow, your turbulence level is in the order of 11 to 12%. So you're not so far off, but you will see later on this kind of turbulence that is generated here is a bit artificial, I would say. And so that is maybe one of the most strong drawbacks you have with this system here. Typically, you need a co-flow in this cross-section that is these parts over here, where you have to purge with nitrogen to prevent mixing with air from the side. Otherwise, if you're looking for a non-premixed flame, that wouldn't work because you would have here then certain heat release zones maybe at the side. Having a horizontal stagnation plane over here means that you have a symmetric influence of gravity, which is good. But then, of course, if you're interested here in this area where you would like to go more or less perpendicular to the turbulent flame in average, you have to send your laser along the symmetry axis. That's doable but painful. Okay. As well, what I mean by controlled boundary conditions, you can imagine if you have here a flame sitting with, let's say, 15 kilowatts or 20 kilowatts or so, everything would be heated up, so you have to water cool the whole system to have a reliable and stable operation for the whole day. Parametric variation could be fuel, composition, or the Reynolds number. And here we see as well a good property of this flame. You can easily drive the system into extinction, and I will show you how. And for that, I will, from this chart, where you see here the parameters, Reynolds number, where you see here the degree of pre-mixing of the fuel. First of all, this has been chosen, similar like in the Sandia flames, that you're not going for fully non-premixed, fuel against air, because then you would have sooty flames. You would like to prevent that. That's why you have here some premixture, that the flame still is bluish, and you avoid the complexity of soot. You're limited in Reynolds number because of the extinction, where the residence time of your fluid elements are too short to release enough heat to ignite the oncoming gases, and that is rather low here. The strain, which is here the mean strain, is here limited to numbers which are relatively low. I will take here one example out of that and explain it a bit more. So typical flow rates, a few meters per second. Turbulence Reynolds number, that is rather low. And that is maybe the drawback of the system, is around 100. Maybe you can increase it to, with a better turbulence grid, to 200. But that is not the exact turbulence level you would face in combustors. As I said, the bulk strain rate leading to extinction cannot be pushed too far, because extinction happens quite early. And you see here how you calculate that. And then maybe a few words more about the problem you have with this turbulence here. Due to the design, the residence time of a fluid element in the mixing layer is here in our case for this situation in the order of a couple of milliseconds, 4 or 5 milliseconds. But the large eddy turnover time, which means how long it takes that an eddy makes a full turn, is much longer. And that means the turbulence has not fully developed. And that's why it is not directly or as in real combustors. And you have to consider that, and maybe not all of the findings are directly transferable. However, what is good about the system, you can control the length scale. In this case, it's here in the order of 5 millimeters. That can be controlled by the hole size. If you increase, for example, the hole size, you would increase as well the integral length scales. What is good about the system, you can fully resolve with our diagnostics the Kolmogorov and Batchelor length scales. Kolmogorov means the smallest scales of eddies. Yeah? Imagine your flow field composed of large eddies that are dissipating into smaller eddies, and the smallest eddies before they dissipate into heat are in the order of 150 microns or so. And the Batchelor scales are the smallest scales that you, for example, have in mixing. And for gaseous flows, they are in a similar order of magnitude. So on the left-hand side, you see the time average photograph. It's not very exciting. If you look from slightly underneath, so imagine you have now a camera looking from this perspective with a bit higher resolution. To the right-hand side, maybe in this projection it's difficult to see, but you see here the nozzle, the upper nozzle, and here you see in slow motion the turbulent flame. Yes, please.
Quick question. The properties of the jet flame.
Yes.
So how do you deal with anisotropies in the flow field, like turbulent anisotropy?
Well, if you take a RAND model, you're in trouble. There as well, you have possibilities to account for anisotropy, but you need more advanced models than the K epsilon. Then anisotropy at the large scales by large eddy simulation is accounted for. But only the assumption is that at the smaller scales you have isotropy fulfilled, which is, for this flame, not sure whether this is really true, but that's the assumption.
But do you measure, for example, also the intruder length scale in all 3 directions?
If you have the time to do that and the money, yes, you should try. Yeah. If you do high-speed PIV, for example, it becomes possible with the restrictions you might have with the spatial resolution. But there you can, in principle, do it. In, let's say, for 2 components. 3 components is really difficult. Yeah. All right. Let's see what happens if you come now closer to the extinction limit. We have now the same perspective. What you see is now, after image intensification with the image intensifier, you see from the same perspective, and these areas with red are high zones of high heat release, and zones going over blue to black are zones with less and no heat release. And if you now operate the flame very close to the extinction limit, you see here how the reaction waves go on. Here was a local extinction. When a local extinction happens in the vicinity of the stagnation plane, you see now how the local extinction goes over into global extinction. And that's a very interesting problem to study. And that happens in gas turbines. Okay, we have the restriction here that the turbulence is maybe not as high as in combustors, but at least you have the optical access and you can try to get an idea what's going on by the interaction between flow and scalar fields leading to extinction. So that's what it's very good for. Okay, before the break, maybe we make one further flame. If you now increase complexity, one possibility is to make the flow field more difficult and thereby advance to systems that are closer to real combustors in terms of the flame stabilization, where you have now not only complex chemistry, still high temperature chemistry, but as well a more complex flow field. And so here you see a possible realization. So interestingly, in premixed combustion, you at least 10 years back, you haven't seen so many examples. That has changed since then. But premixed combustion, of course, is due to the potential for low NOx, the more interesting for the future. And here you see a realization where this is as well a cross-section of the system, where you have here a radial swirler with an annular slot surrounding a bluff body, which is temperature stabilized. And inside here, there is a possibility to change the swirl. And the swirl level, of course, the Reynolds number as well, can be changed. The swirl number, you might know this definition, is the ratio of the axial flux of the tangential component relative to the axial flux of the axial momentum component. And so that can be changed in this so-called movable block design, where you can have two components that can be rotated against each other, where you have either for swirl number 0 only a radial inlet, or if you increase now the angle between these two components, you can add here a tangential component. And due to the way it's designed, there is a certain limit, so the geometrical swirl number is 2, which is already very high. So in typical combustors, you're more on the order of 1, for reasons that become clear in a second, because you, in premix combustion, end up with flashback otherwise. Yeah, as I said, flame series is important. You have to vary parameters. Here, the Reynolds number has been varied for a constant swirl number, although you can as well take a constant Reynolds number and change the swirl, and you will see an example later on where you can drive the system into flashback. Of course, if you do have now here different Reynolds numbers, then you have as well different thermal loads, and already with a thermal load of 150 kilowatts, it's huge. Yeah? Although the flame stays small, you need a good lab infrastructure to get rid of that heat. And as I said, you cannot put the exhaust system directly on top of that. That would influence the flame too strongly. And so we measured that. So roughly, at least to the design we have, with a meter of a huge ventilation system in between, it's roughly in the order of 50% that goes out due to radiation, even if you have a lean premix flame, because there's so long residence time. And then you have to cool your lab. How do you do that? We solved it by double walls. We have the brick walls, and then there is some metal in front of that. And because we couldn't afford to cool the metal by water cooling, we have then a strong flow of air going between the brick and the metal wall. And then we just open 4 windows in the top of this house, which is a house in the house, and then release the heat to the larger environment. And that is where then university has to care about it. So by that, we keep the cost more or less controlled. And look at the Reynolds numbers. It's not very impressive. 40,000 for 150 kilowatts. And it's only to start that people from CFD say that is sufficient. And look at that series. We could show that, well, the asymptotically, the characteristics of the flow field, for example, come to the same if you normalize them appropriately. Those behave not so differently, but the Reynolds number of 10,000 is too small. It's too small. And that makes it problematic if you don't have the facilities available. If you're looking into premix flames, one of the first questions of your supervisor or reviewer would be, what is the classification in the regime diagram, showing here the normalized velocity fluctuations, normalized with the laminar flame speed as L, over the normalized turbulent length scales, normalized by the laminar flame thickness. And you might have seen this diagram where you have here the laminar flames. Here you have wrinkled flames where the turbulence is not changing anything to the flame structure, as well in the corrugated flames. And with Reynolds 10,000, you're in a regime where you know everything about the flame structure, which is shown over here. It becomes more interesting if you go for the higher Reynolds numbers, where you then are in the regime of thin reaction zones. And there it's believed that the eddies are getting in the size so small that they cannot interact with this reaction zone, which is for atmospheric conditions for methane air combustion, maybe here in the order of, let's say, 100, 200 microns. But they can penetrate the preheat zone and there change the flame structure. And that's why it's interesting to look into this regime. However, modeling is not so bad still for this area. It becomes more and more interesting if you go towards the broken reaction zone, which has not been really, this is a theoretical model, but good experimental evidence about the flame structure at this high turbulence level is still an open task. Yeah? People have shown some imaging work about it, but really the flame structure to resolve what it looks like that needs Raman-Rayleigh spectroscopy along a line and is still an open topic. The flame doesn't look very impressive. It's a swirl-stabilized, lean premix flame. It becomes more interesting if you know, let's say you have studied that and you have a lot of information about the parameters of interest. There is something which is nicer to show than that. And that is the transition to flashback. That's a huge problem in lean gas turbine combustors. Where you can drive into flashback is either increasing the swirl number. That's why it's good to have this movable block design. You can do that stepwise. Or you starting from lean flames, you make them faster, increase the laminar flame speed and thereby the turbulent flame speed by going step by step towards stoichiometric conditions, where you, as you know, the flame burns faster. And to look at that problem, you just have, after some empirical investigations, we just extended here the bluff body over the nozzle exit by, in that case, a couple of 10 or 20 millimeters, I think. And then you see that for a given equivalence ratio, let's say 0.8 or so, with no swirl, the flame stabilizes, maybe difficult to see, here's the bluff body. You see the flame stabilizes downstream. Because of heat transfer, there's a certain liftoff on its own. Very interesting what's going on here. However, now you increase the swirl and the flame comes down, it goes to the shell and it starts to spin around the bluff body. If you then go over a certain critical swirl number, eventually the flame flashes back and it burns inside the nozzle, and then you should better switch it off after a couple of seconds. Otherwise, you would melt everything inside there depending on the material. And so that is shown here again in high-speed movies in slow motion. That is now this precessing flame. Oops, what is happening here? That's strange. It moved up. Okay, maybe after the break I'll show you the movie directly. What you would see is a spinning flame around that bluff body. Hopefully that is working here on that side. If you look from above over from the top, you see how the flame goes round, and here where the bluff body is, there is actually no flame luminosity, everything at the side. And then eventually, if you do it too badly, then the system can flash back, and hopefully this video shows that. Here you see where the bluff body is. You have optical access to that, meaning that the surrounding of the nozzle is made of quartz, and you see chemiluminescence imaging at high speed, where the flame precesses around, and somewhere is in the nozzle, but not yet flashed back. And now it's the interesting part to understand why suddenly the system goes into a flashback. Yeah, a very, very complex problem. Yeah, and then it takes only a few rounds, and the system is anchored then by the radial swirler inside the nozzle. And when that has happened, another interesting problem occurs. You see here in slow motion how the heat release is changing in time. So you have a thermoacoustic phenomenon. So the flame couples with the volume of the nozzle. And so I'm not an expert in that, but that's a different problem in lean premixed gas turbine combustion, where you can see for different phases. And here high-speed imaging, although qualitatively, can provide insights that are really, really interesting to study and to understand the coupling between heat release and these oscillations due to the volume. And here you see a bit more about it, how the spinning flame goes over into flashback. If you follow these leading edges over here in space and time, you can try to find out what is the reason that suddenly the system, although it might be stable for a couple of seconds, then suddenly changes and goes back into the nozzle. And so you need multi-parameter diagnostics, and that's only a first step. Here, what you see in this animation in a second is, although I have not yet explained the techniques, is where you have here the bluff body, here the outer nozzle, which is made from quartz, send in the laser as a sheet, measure the velocities, which are shown here, red, high velocity magnitude, white, zero axial velocity, purple is negative axial velocity. And what you see here is the flame front taken from OH imaging, for example, or if you take an aerosol for particle image velocimetry to be discussed, the vanishing of the particles by burning them, you can identify where the flame is. And interestingly, for many of these cases, we have observed that at the leading edge, there is a velocity component going in upstream direction. So something like a recirculation, which somehow sucks the flame into the nozzle. And that is shown here now in space and time. from one flashback event where we are able to follow that in this system to see what actually is happening. So at least we could see the phenomenon and build up a model that allows to better understand what's going on. And initially I didn't believe my PhD that he came up with, and I'll try to check that, of course, by things looking at the raw data. That's maybe the most important part. What you see here is me scattering from oil droplets that are seeded to the flow. Here's the bluff body, somewhere here is the wall, the outer part of the nozzle. And here you see now by evaporation how the flame comes closer upstream, and look at these particles. They go negative in axial direction. And so if you see that by eye from this raw data, then you can start, I think, to believe that your post-processing is okay. Of course, you come up then with a hypothesis. Why is that happening? And that's still ongoing. It's not really solved. Of course, if flow goes upstream against the bulk flow, there must be somehow an adverse pressure gradient, a pressure gradient that drives it. And ideally, what you would like to measure is then the pressure distribution. How to do that? I don't know. The only thing, spectroscopically at least, I don't know it. So what we came up with is simple, to drill holes into these bluff body, and then try to connect pressure transducers. And partly we failed. At least one pressure transducer has been installed. We couldn't really prove that we observe an adverse pressure gradient, but at least what you can see here nicely is how the system behaves when the flame passes by. You have pressure fluctuations that are as well strongly influenced by combustion. However, it is not so clear from the single pressure measurement that you have an adverse pressure gradient. So that's still to be proven, as I said, but it's interesting to see when the flame is then flashing back, what's going on here. The amplitudes of the pressure oscillations become huge. And this is the case now here. The flame passed by, and then you have a huge, strong sound due to thermoacoustics. And so a very interesting field, I think, to combine flow and flame measurements in the sense to see where the flame is actually in space and time, and combine that with pressure measurements. And finally, of course, that is what then industry people are interested in for a certain geometry, how the stability map looks like. And that can be done, for example, if you have here for a fixed Reynolds number, you go from a lean flame and step by step make it richer, and then you see how the flashback is reached. You repeat that many times and take up the mean value for that respective Reynolds number, and you can come up with a stability line over here that can be as well put into a simple model for scaling, for example, although doing that by LAS, for example, would be not yet really feasible. And we see that lower Reynolds numbers, look here, 6,000 against 10,000, lower Reynolds numbers favor flashback. I think that's understandable. Yeah? The smaller the bulk velocity against it, the higher the probability for flashback. And of course, the higher the laminar flame speed is, those flames are as well more prone to flashback. So simply, for example, adding hydrogen to a system that has worked stably for natural gas might end up in a disaster. Okay, not shown here is the independency of the swirl intensity. Okay, I think we have now a break, 15 minutes if that is okay, and then we will continue with this benchmark configurations with example number 3 and 4. Thank you.